Calculus, Chapter 7, Section 2, Matrices. We learned a little bit about matrices in Algebra 2, and so we're just going to start with that idea and add a little bit more into it. Matrices can be used to store data, and we talk about the order of a matrix or the size of the matrix, an M by N matrix. M are the number of rows in a matrix. 1, 2, 3, 4, whatever it is. However many rows. There's our rows. And N, the second number, the number of columns in that matrix. So 1, 2, 3, 4, 5, however many columns. Rows and columns. Every entry in the matrix, or element in the matrix, can be designated by the number of the row and the number of the column. So that entry A sub 12 is on row 1, column 2. That's all that means, A sub 12, row 1, column 2. So we can locate any position. That's what they are saying right here. First number is the row subscript, second number is the column subscript. So every element or entry. So if I said A sub 32, we would know it was in row 3, column 2. That easy. So that size of the matrix is called the order of the matrix. So if I have a 2 by 3 matrix, it has 2 rows and 3 columns. A square matrix. Well, if a matrix is square, it means I have exactly the number of rows and columns. 3 by 3, 17 by 17. That'd be fun to work with. Equal matrices. For two matrices to be equal, every corresponding entry must be equal. 2, 3, 7, -4, 8, and 13. Tell me the order of this matrix, by the way, that I just wrote. The order of the matrix, 2 by 3. I wrote a 2 by 3. There are 2 rows and there are 3 columns. If two matrices are equal, it means every corresponding element or entry is equal. So if there's a 2 in row 1, column 1, there needs to be a 2 right here. If there's a 3 here, there needs to be a 3 here. If there's a 7 here, there needs to be a 7 over there. Well, that works. 14 divided by 2 is 7, so it's still equal. You get the idea. X is what? -4. Yeah, you get the idea. All right. Determining the order of a matrix. Tell me matrix A. 2 by 3. B. 4 by 2. Boy, this is hard pre-calculus, isn't it? C. 3 by 3. So it's also called a square matrix because it has the same number of rows and columns. Well, we learned how to count, so moving on to the second page. Matrix addition and matrix subtraction is just as easy. If I want to find the sum of two matrices, it simply means I will add together the corresponding elements. First row, first column, plus whatever's in the other first row, first column. Same idea on the difference of two matrices. So let's come down here to this example. Wow, nice big matrices. Matrix A, here's matrix A, gives the mean SAT verbal score. So how well did you score on your verbal part of the SAT if you took it? For the 6 New England states over the time period from 2001 up to 2004. So the states are in the rows and the years are in the columns over there. Matrix B gives the mean SAT mathematics score, which of course we're more interested in that one. Yeah. For the same 4-year period. Express the mean combined scores for these New England states from 2001 to 2007. Well, it means I need to add these two matrices together. So let's see how good a job they did. Let's pick this spot. Tell me the location of that spot. 43. A sub 43. Row 4, column 3. So I need to go row 4, column 3. This one. And if we take 522 plus 521, that would equal how much? 1,043. So if we go to the 4th row, 3rd column, sure enough, 1,043. All it takes to add or subtract is to add or subtract the matching or corresponding elements. Scalar multiplication, that's easy. Scalar multiplication is just as easy as well. Scalar multiplication means I multiply a number times a matrix. Consumer Advocacy Group has computed the mean retail prices for brand name products and generic products. So here are the stores in our rows, and we have a brand name product at each store, and then a generic product at each store, and there are the prices. And let's see, the prices are shown in the 3x2 matrix right here. City has a combined sales tax of 7.25%. So it says construct a matrix showing the comparative prices with the sales tax included. So if I'm going to include the sales tax, I'm going to have to multiply by 1.0725. And so all we do to multiply is it's just like distributing. We are going to multiply this value times every single entry or element. That's scalar multiplication. You just take whatever on the outside and multiply it by every single element. You get the new things. Some more definitions here. Zero matrix. Well, this is not too hard to figure out. I am going to make a 2x2 zero matrix. What is inside that matrix? There you go. It's a zero matrix. Additive identity. Let me start with numbers. If I have the number 4, what would I add to that number 4 so I get 0? -4. I would add -4. I am sorry, that's not what I wanted. That's true, what you just told me, but that's not what I wanted to do. What would I add to that 4 so it stayed 4? 0. You would add 0. So guess what? If I have any matrix and I add to that matrix the 0 matrix, what do you think happens? It just stays the same. That is the identity. So the additive identity is the 0 matrix. You add 0, nothing happens. Now, back to that exciting thing I was doing a minute ago. The additive inverse. Let me do that same thing. 4 plus what is a 0?
-4.
A -4. So there is an additive inverse for any matrix. If I had the matrix 1, 2, 3, 4, what would I need to add to that so I got the identity matrix for addition? Yeah, you guys are just geniuses. There you go. You figured it out. Matrix multiplication. Now, before I do that, what's the order of this matrix? 2 by 2. What's the order of this matrix? Do you think we can add 2 matrices together that do not have the same order? No. Nor can we subtract them, because we need to have matching elements all the way across. And if they're not the same order, we wouldn't have matching elements. So that's just something to keep in mind. Now let's have a little more fun. Matrix multiplication. Matrix multiplication is saying the product of 2 matrices, in order to get any element, in order to get any answer, I have to do this. What in the world does that say? Well, I don't know either, but I can explain it down here. It says I have to take the row times the matching column. You notice this is I, 1 right here, and this is 1, j. So this is row I, column 1, row j. What does that mean? When I multiply these 2 matrices together, there are actually a couple of things that have to be true. The first thing is, let's take the order of this matrix. What is that order?
1 times 3.
It's a 1 by 3. What is the order of this matrix?
3 by 1.
It is a 3 by 1. You may remember that these middle numbers must match if we are going to multiply 2 matrices, which really means the column in the first must be equal to the rows in the second. And then the outside numbers, the rows in the first and the columns in the second, will tell us the order of our answer. This is going to be a 1 by 1 matrix, which means it's just one number, is what this one is going to be. So now let's go through how I multiply. We multiply rows times columns. And I can remember it because that's exactly the same way we write the order of a matrix, row by column. I have to take the first thing in the first row and multiply it by the first thing in the first column. So this answer is going to be 1 times 4, 1 times 4, and then 2 times 5 plus 2 times 5 plus 3 times 6. 3 times 6. That is the whole row times the whole column. And what do we get? 4 and 10 and 18. 14 plus 18, 32. And it's a matrix, and so we have these nice little brackets. There's our answer. It's a 1 by 1 matrix, 32. So when I have a row matrix, it's called a row matrix because it's only a row, times a column matrix because it's only one column. A row matrix times a column matrix is just going to be one number, or a matrix with one entry into it, a 1 by 1. So let's make them a little bigger here and see if we can find the product of A times B. What's the order of this matrix? In this matrix. So can we do it?
Yes.
And the answer is going to be a 2 by 2 matrix. So the steps that I do, and I think it will help you since we know it's going to be a 2 by 2. I know I'm going to have 2 rows. I'm just going to start my 2 rows. I do a set of parentheses, and I am going to work on my first row and my first column and just write the answers in this first set of parentheses. So 2 times 1 is 2, 1 times 0 is 0, and negative 3 times 1 is a negative 3. Now that is going to be my row 1, column 1 answer. I'm going to stay with this row 1 and come over to column 2 now. So now we're working on this one. So negative 8, first numbers will be negative 8, plus 2, and plus 0, minus 0. And I am done with the first row because I have multiplied by both my columns. So here I can see I have my first row all done, and there are going to be 2 columns in it. So we'll come back now, second row, and first column, we're back there. So first numbers? 0, then 0, then positive 2. 0 plus 0 plus 2. And stay with the second row and back to the second column. 0, 2, 0. 0 plus 2 plus 0. And now I'm going to get my answer. So first row is going to be what? Negative 1? Negative 6. Second row? 2, that's a 2. And 2. There we go. And it's a 2 by 2, just like we knew it was going to be. Let's try this one. 2 by 3. 2 by 2. Can we multiply? We're done. Not possible. We don't want very many of those because that's boring. Using matrix multiplication, a florist makes 3 different cut flower arrangements for Mother's Day. Arrangement 1, 2, and 3. So here are her beautiful arrangements. Each involving roses and carnations and lilies. So the flower arrangement 1 takes 5 roses, 6 carnations, and 4 lilies. You get the idea. Matrix A shows the number of each type of flowers used in each arrangement. The florist can buy his flowers from 2 different wholesalers, wholesaler 1 and wholesaler 2, and here are the prices for roses, carnations, and lilies from each of those wholesalers. Construct a matrix showing the cost of making each of the 3 flower arrangements from flowers supplied by the 2 different wholesalers. Well, we know the idea is I want to take the number of roses times the price of the roses, number of carnations times the price of the carnations. But if I took this and threw it just up here as it is, so I would have tell me the order of this matrix.
3, 2.
This is a 3 by 2. What's the order of this matrix?
3 by 3.
This is a 3 by 3. Now, just looking at the order, can I multiply these together?
Yes.
I can. But let's look at what I have. I have, wholesaler 1, wholesaler 2, and I'm just going to put rose, carnation, lily. It's a price. But notice if I took this row and multiplied it by this column, I would be saying 5 roses times the price of roses. So far, so good. 8 roses times the price of carnations. That's not going to help me. So what we want to do is transpose one of these matrices. So right down here, they transposed the first matrix. So what does it mean to transpose? I switch the rows and columns. It went from having roses, carnations, and lilies, and the 1, 2, 3 arrangement to be just opposite. 1, 2, 3 arrangement, roses, carnations, and lilies. And now if you look at this, I would have rows in 1 times rose price. Carnations in 1 times carnation price. Lilies in that 1 times the lily price. So it does exactly what I want it to do. Go to your calculators. And let's introduce to matrices on graphing calculators. You notice you have a matrix button right above that inverse button next to the negative first. So I'm going to hit second and hit that x to the negative first button. And I am going to select matrix A. And we actually, let me come back up here. We're going to call matrix A this first original one right here. First original one. So it is a 3 by 3 matrix. Hit enter on A. I am sorry. Go back. I just told you to do the wrong thing. I need to edit the matrix. Go over to edit. Hit enter on A. We need to edit matrix A. We need to tell it the order. It's a 3 by 3. 3, enter, 3, enter. And now it will change to represent a 3 by 3. Okay? So now I'm going to enter the 5, the 8, the 7. When I hit 5 and enter, it will run across the row. 8, enter, 7, enter, and then I'll jump down to the second row. 6, 6, 7, 4, 3, 3. So that is how your calculator represents a matrix. Now we need to quit out of this. Unfortunately, it's a little cumbersome, so we have to go back to quit to get out of it, and then go back to matrix to get back into it. Go over to edit again, and let's come down to the second matrix, B, and we are going to enter in our prices for these things. So I'm going to hit enter on editing matrix B, and it is a 3 by 2, isn't it? 3 by 2. And so 1.5, and it does the rows, 1.35, and then it jumps back in. And I'm going to quit. I have in my memory now matrix A and matrix B. Now we already figured out that we had to transpose this first matrix in order to use it. We want to transpose that matrix and multiply it by the other. So A transposed times matrix B is what we are going to do. So let's see how to do that. We'll go back to matrix, second matrix. Now on the name, we're going to select the name. So I'm just going to hit enter. Now I've just selected matrix A. Now I need to go back to my matrix menu to tell it to transpose A. So second matrix, math, arrow to the right, and notice choice number 2 is to transpose a matrix. Enter. Now, oh, I've transposed matrix A. Times, I'm going to hit times. I don't even think you have to. And then I'm going to go back to matrix, second matrix, and with the name, I'm going to select matrix B. So there I finally typed it out. I'm going to take the transposition of A and multiply it by matrix B, and now when I hit enter, we should get the same answers as they got right over there. So we have multiplied those two matrices together. There's the work that goes along with it. But we're not going to be stuck with calculators. Once in a while, you know, we might use them to check some things. Identity matrix. When I am talking about multiplication, now a minute ago we had the additive identity. If I add 0, it doesn't change it. Additive identity. What do you multiply by that doesn't change? 1. I need to multiply by 1 is the idea. If I take 3 times 1, it stays 3. So 1 is called the multiplicative identity. Well, for matrices, we have a matrix that's an identity matrix for multiplication that is just like 1. And notice here is the 2 by 2 and the 3 by 3 and the 4 by 4. You notice any pattern to it? What does it have? It has this diagonal of 1s. sometimes called an echelon of ones. So I've got ones here, everything else is 0. That's the identity. If I take any 2 by 2 and multiply it by this first identity matrix, it will stay the original thing. It won't change it, etc. So this is called the multiplicative identity. So if I take a matrix, let's talk about the inverse. Let's talk about the inverse. Let's use numbers again. 4 times what will equal the identity for multiplication? 1 over 4. Now, sometimes we call that the reciprocal in math. It also is the multiplicative identity for 4. 4 times 1/4. It's multiplicative identity. Sorry, its inverse. Use the wrong thing. 4 times its inverse gives us the identity. So 4 times 1/4. 1/4 is the inverse of 4, the multiplicative inverse. That's the idea of what we're doing here. 4 times 1/4 is 1. 1/4 times 4 is 1. We can do it either way. We'll get 1. So if I have some matrix A, and there is a B matrix that is its inverse, multiplicative inverse. So if I go A times B, or if I go B times A, both ways it will give me the identity. And that inverse is an important matrix to help us solve matrix equations. We write the inverse like this. So that's read A inverse. Matrix A inverse. All matrices don't have inverses. Just like all numbers don't have inverses. What's the inverse of 3? 1/3, right? Give me 1. What's the inverse of 0? It doesn't exist. Everything doesn't have an inverse, a multiplicative inverse. This one doesn't exist. Same thing with matrices. If we have, and only square matrices have inverses. If we have an inverse, it's called non-singular. If I do not have an inverse, it's called singular. It's a singular matrix. So non-singular matrices have inverses. Now I just use a word there. If we're talking about one matrix, we say matrix. If it's plural, we say matrices. So there's English for you, right, Jackie? All these strange ways of doing things. Verifying that we have an inverse. If I want to verify that I have an inverse, I need to be able to take matrix A, 3, -2, -1, 1, multiply it by matrix B, which they claim is the inverse, 1, 3, and when I am done, it should be the identity. And it must work the other way. 1, 2, 1, 3, 3, -2, -1, 1. Both of those should give me the identity when I'm done. Well, let's do this real quick. That's not too hard. Row times column. So first numbers would be 3 minus 2. 3 minus 2. Let's stick with that first row and go to the second column. 6 minus 6. 6 minus 6. Second row, first column. -1, 1. And second row, second column. -2 plus 3. -2 plus 3. So when we do this, I get 1, 0, and 0, 1. Right down here, same idea. I'm going to preset up my 2 rows and 2 columns. First row, first column. 3 minus 2. 3 minus 2. First row, second column. -2 plus 2. I know the suspense is killing you. Second row, first column. 3 minus 3. And second column. -2 plus 3. Whoops, -2 plus 3. So what did we get? That verifies we have inverses of each other. Now you might say, I'm going to enter that in my calculator. Well, you could, but you know what? It takes you just as long to enter in your calculator as it does to do this right here. It's a little cumbersome on these graphic calculators entering these matrices, but sometimes it's real important for us. All right, the next thing we have with matrices is determinants. Square matrices have determinants to them, which is one number, and that one number tells us things and can be used in calculations. So if I want to find the determinant of matrix A, that may be one way we write it. Or I can write my matrix with these bars. Notice it's not a bracket, it's just those two bars. They look like absolute value bars, I guess, kind of. But those two bars, so those are determinants. And the formula, you may remember, I multiply A times D, minus C times B. Or BC, doesn't matter the order you do it. So let's try out an inverse, a determinant. 2, 3, negative 7, 5. So if I want to find the determinant, and I want to say I'm finding the determinant, not just say the matrix, I know I'm going to go 2 times 5 minus negative 7 times 3, or 3 times negative 7, take your pick, I guess. So what do we get? 10 plus 21? 31 is the determinant of that matrix. We need the determinant in order to help us find an inverse of a matrix. And we are going to learn how to get the inverse by hand of a 2x2 matrix. So in order to get the inverse of a matrix, notice that's the notation for inverse. The inverse of some matrix. We are going to go 1 divided by the determinant. That's the determinant formula. And then we rearrange this matrix. Look at this diagonal and this diagonal. What has happened? Switch them. And then if I look at this value and this value, this value and this value, what did they do? Become negative, or they change the sign. It is the negative of what it used to be. The negative of a negative would make a positive. So let's try and get an inverse. Oh, wait a minute. Prove that this matrix is singular. In other words, it has no inverse. Well, here's how we can prove it has no inverse. The determinant will answer that question for us. Since this is the formula for the determinant, what can you not divide by? 0. If my determinant is 0, I can't do that and find the inverse. I can't get an inverse. So that's the deal. Is it equal to 0? If the determinant's equal to 0, then it's singular. I can't find an inverse. So my determinant, 6 times 1, 6 times 1, minus 2 times 3. Well, guess what we get? 6 minus 6 equals 0, no determinant. It's a no inverse. It's a singular matrix. So this is a 2x2 method of finding an inverse. I should go through and find an inverse. That's probably why I have all this big space back here. I just did this one. This has an inverse because that determinant was 31. 2, 3, negative 7, 5. 2, 3, negative 7, 5. Let's figure out what the inverse of this matrix is. 1 divided by the determinant. 2 times 5 is 10. Negative 7 times 3 is at negative 21, so we're adding that 21 times. Then I'm going to rearrange the 2 and the 5. I'm going to change the signs on the negative 7 and 3. Now this is 1 over 31 times this matrix, 5, negative 3, 7, 2, which means scalar multiplication. I need to multiply each thing by that. I'm going to make myself a little more room. 1 31st, 5 31st, minus 3 31st, 7 31st, 2 31st. There's the inverse. And if you wanted to, you could stick it in your calculator, multiply it by that matrix B, and it would equal the identity. 1 0 0 1. So a 2x2, fairly straightforward method of getting the inverse and getting the determinant. Fairly straight method of getting the determinant. So what if we go bigger than 2x2s? What if we want to do a 3x3 or a 4x4 or our favorite 17x17? I'd hate to do that by hand. We can use the cofactor method of getting a determinant. So determinant of any square matrix, you can actually use it on a 2x2, but this is longer, so we do the other. The determinant of any square matrix can be found using this process. We have something called a minor, and we have then a cofactor that uses the minor. That's the minor. This whole thing is called a cofactor. And all their notation is true. I'll explain their notation and come back to this, and we'll see how it makes sense. First of all, when we have any square matrix, I want to decide which row or which column we are going to expand the minor and cofactors on. Expand the cofactors on. So they have decided, what did they say? Second row. They have decided to use the second row. It doesn't matter. You can use the first, second, third row, first, second, third column. The process is the same. You get the same answer. So they're using this. That means we are going to have to take this value times its cofactor. That's what they're showing. Then this value times its cofactor. And then this value times its cofactor. That's the idea. So how do I do that? Well, a sub 21, let's color code. Whatever that is, that number goes here. Times negative 1, and it's always negative 1, and it's raised to the 2 plus 1 power. I add those two numbers together. That's what it meant right back here, to the I plus j power. Negative 1 to the I plus j power. Then I have the determinant of the minor, which is, I'm going to cross off the row that this number is on, a sub 21, and the column that it is on. And what is left is the minor determinant that I want to find. A12, A13, A12, A13, A32, A33. There it is. Then I go over to the second one. Here it is, the second one. Times negative 1 to the fourth now, because 2 plus 2 is 4. Times its minor. If I cross off the row and the column that it is on, what is left is the minor determinant I have to find, etc., all the way across. So this looks like fun. Let's try it out here on part B. I guess we'll do part A first. It says, finding inverses. Determine whether it has an inverse, and if so, find that inverse. Okay, so we're going to determine if this has an inverse. Well, we determine it has an inverse by finding the determinant of it. So 3 times 2 minus 4 times 1 is going to be 6 minus 4, which is 2. Check. Has an inverse. So I can use that previous formula to find the inverse. It's going to be 1 over the determinant. Well, 2. Already did it. Times, and then we are going to rearrange to 3, negative 4, negative 1, and we have to multiply it all by 1/2. So what do we get? 1, negative 1/2, negative 2, 3 over 2. There's our inverse. Now we need to determine if this has an inverse by checking its determinant to make sure it's not 0. We can choose any row and any column. I'm going to choose the first column. Now in the future, you're actually going to want to choose something that has 0 in it, because when you multiply by 0 in one of your steps, it's just gone. It's going to save it. But we're learning here. All right, so I need to take 1 times negative 1. This is the first row, first column, squared. Times its minor. So I need to, at least in my mind, if nothing else, cross out the row and column that 1 is on. Negative 1, 3, 0, 1. Plus, and now I'm going to move to my next number, 2 in that column. And then negative 1, well that's row 2, column 1, 2 plus 1 is 3, cubed. And its minor, I'm going to cross out the row and column it's on. 2, negative 1, 0. Plus, I go down to my last one, right there, negative 1 times negative 1 to the, you tell me.
3 plus 1.
It's the third row, first column, 3 plus 1 is 4, to the fourth. It'll always go in order, wherever you start. 2, 3, 4, it always goes in order. But anyway, Now its determinant, cross off the row and column, 2, -1, -1, 3. Now remember, each of these are determinants. These are minor determinants. They are a number that I need to figure out. Well, let's start through it. 1 times -1 squared is 1. 1 times 1 is 1. So it's 1 times, let's see what we'll get. -1 times 1 minus 0. I'm just going to write it there. We'll come back. Plus, let's see, -1 cubed is a -1. 2 times -1 is -2 times 2 times 1 is 2 minus 0 again. Plus, -1 to the 4th is a 1 times -1 is -1 times this determinant. 2 times 3 is 6 minus -1 times -1 is a 1. So what do I have? -1 here plus -2 times 2, -4. Plus -1 times 5, -5. -1 and -4 is -5 plus -5 is, woohoo! There is the determinant of that thing. Now let's find the inverse. Well, you know what we do? We do it in the calculator. It's what we do. So I am going to go to my matrices. I want to edit a matrix. I'll just edit this first matrix. And I need to see those numbers that I had covered up. And, oh, it's a 3 by 3, so I'm good to go. 1, 2, -1. 1, 2, -1. 2, -1. 3, -1, 0, 1. So I'm going to enter in my matrix. I happen to do it in A, so I'll need to remember that. Quit, have to get out. Then go back into matrix. And I'm going to use that matrix, A, to find the inverse. X to the -1st. Inverse button. And say enter. And it says, here is your inverse. Oh, look at what I remembered to do last time that I didn't do this time. Let me go back and do that. I'm going to name my matrix. I'm going to take matrix A. I'm going to say I want to find the inverse. Hit your math button, and choice 1 after you hit the math button is convert to fraction. So I want to do this, but I want it converted to fraction form, because I don't know that 0.1 is 1/10, but now I do. 1/10, 1/5, -1/2. Those dots on the end, in other words, scroll to the right. It was too much to fit on the screen is all they're doing. They're having you scroll horizontally. You can scroll left and right. So there's the inverse of this one. 1/10, 1/5, -1/2, 1/2, 0, 1/2. So anyway, we use the calculator on that. By far the easier way to get the answer. Almost there. Properties of matrices. Can I add, multiply, rearrange it? What can I do with it? What are these properties? Commutative property says I can change the order. Now we can change the order of addition of matrices and it's just fine. A plus B, B plus A, doesn't matter. Same answer. Not multiplication. You cannot say matrix A times matrix B is the same thing as matrix B times matrix A. That is not necessarily true. It's possible, but not usually. It's not usually true. So the commutative property for multiplication does not hold true for matrices. Identity property, add 0 matrix, multiply by the identity matrix, we have those things. So that's good. We can use the distributive property. I can take that matrix A and distribute it here. We can distribute from the left, we can distribute from the right. Distributive property works. Associative property works for both addition and multiplication. I can group them differently. If I'm adding them all, I can group them differently. Multiplying them all, I can group them differently. That's okay. Don't change the order. That's commutative. That doesn't work. Inverse, that works. We have an inverse matrix for addition. We have an inverse matrix for multiplication. Gives us the identity when I do it. So, and we can distribute whether we are adding or whether we are subtracting. I'm not sure why they split that apart, but we can just use the distributive property. So really the thing to remember is this. Don't change the order of the matrices when you're multiplying them just because you like it. It won't work. You'll get the wrong answer. Has to be in the right order. One little application from this section of how matrices can be used. We are going to reflect a point. Prove that the image of a point under reflection across the x-axis can be obtained by multiplying by this matrix. Well, a point is some x and y value. So if I have some x and some y value, there it is, xy. If I am going to reflect it across the x-axis, it is going to be the point right down here, which is over x down y. Negative y is what it's going to look like when I'm done. So I should get an answer that looks like this when I started with the xy. So let's start with a matrix and call it the matrix xy to stand for the points. And multiply it by this reflection matrix that they claim is going to work. And let's see what happens. Now, I guess I made that a little too big. This is a 1 by 2. This is a 2 by 2. It works to multiply, and the answer is a
1 by 2.
1 by 2. We're just going to get a 1 by 2 matrix. One row, 2 columns in it. So, x times 1, I get x plus 0. X plus 0. Stay with that row, go to the second column. 0 minus y. 0 minus y. And guess what that is? X, I shouldn't really put a comment in there, x, y. Or that can be understood as the point x. Negative y, x negative y, which can't be understood. So when you're doing your computer programming and you want to flip things around on the screen, well, the math behind the monitor, the math behind the picture you see, and that's how it works. There's math behind. Start talking about video games, moving things around. There's math on the back end that makes that stuff all move. I'm done. Your turn.